Hello, mic check. 1, 2, 4. It's missing 3. Good afternoon, everyone. Welcome to the talk. It's amazing. If you chose my talk over Barcelona, that means a lot to me. Thanks a lot for being here. It's 5 p.m. Thursday evening, and you're in my talk, not outside. That means a lot to me. Thank you so much. Now, when you begin the talk, everyone's very happy and they're smiling and a lot of good things happen. You don't know what happens towards the end of the talk, right? So why not just take a picture when we are all happy? All right, so why don't we just raise like 2 hands so that I can say that there were like double the number of people that were here. Awesome. I'm already in love with all of you. Great audience. Sweet. So we're going to talk about the best practices for scaling web apps. The first 60 to 70% of my talk is going to cover a lot of things that you see outside, like horizontal scaling, vertical scaling, scaling out, scaling up, vertical partitioning, a lot of that stuff. So we're going to cover what we hear about, what we end up doing, and we're also going to cover what we don't hear about a lot, but it happens when you have a real situation in real life. For example, we're getting 1 billion hits a day. We got to do the best things, right? So that kind of stuff is going to be towards the end of the talk. That's the next 30%. And we're also going to have demos, so it's going to be a fun talk. It's a lot of slides, so please don't mind. The font's pretty good. I hope you're going to have a lot of fun with it. What am I not going to cover? If you just Google best practices for speeding up your website, the first article written by the exceptional performance team, I think at Yahoo, is an amazing article. And it looks like there's a bug in Google Chrome. The article just doesn't pull up, but it's an awesome article. We're losing internet. We just got hijacked by Google. Is that serious? Awesome. So it's up right there. Pretty good. So we're not going to cover. Am I having a really bad internet connection over here? Well, you know what? Just trust me on this. You surely want to check this article because it tells you how to minimize your HTTP requests, what do you want to do when it comes to images, CDNs, a lot of good stuff. And the reason I'm bringing this up is because I'm not going to cover all this. We're going to specifically focus on scalability aspects. So back to the PowerPoint. It's more reliable than the internet. Right after this, we're going to have the Ask the Expert session. I think it's in Hall 5. If you want to talk to me, I will be available at table 41. You'll also have snacks and beverages. Agenda for today. We're going to talk about why is it important to scale. We're also going to talk about how to create a scalable solution. And as a developer, what I'm going to do is create a while loop. And if it is not fixed, I'm going to start with proposing an architecture, identify the single points of failures, and then identify downtime and apply a better solution. And we're going to keep doing this until we end up at a good solution, at a decent enough solution. This is a slide that changed my life about 7 years ago. Amazon claims that just an extra 1/10 of a second on their response times will cost them 1% in sales. And that's billions of dollars. Same with Google. It says half a second increase in latency caused their traffic to drop by 1/5. Again, that's multi-billion-dollar in revenue. Now, that's like my month's salary. And it's important, right? It's important when it's billions of dollars involved. We have to look at these numbers as they are very significantly important numbers. And 1/10 of a second is nothing but 100 milliseconds. If you look at 40 milliseconds, which is usually the latency, we're left with 60 milliseconds to get the query done. And it's not very easy. We're going to look at techniques on how we can make it happen. Why is scalability important? I don't know if you followed Instagram on the day it was launched. The website was down. There were so many hits that the website was down. It was the fav icon. In today's world, we have billions of devices out there. We've got about a population of 7 billion people in the world. I think about 3 billion of them use internet actively. And everyone's got like few tablets, cell phones, and devices, like even laptops that still exist. So what's a number? What's a good number that you want to work towards when you create your website? Do you have a number in mind? What's a safe number? So if you were to say, my website is not going to go down, what is a number that I would want to create a website for? Would I want to scale it to 1 billion hits a day? Or 10 million hits a day? What's a good number? What was that? It depends, yeah. It totally depends on your website. But what's a very safe number? We just said the population of the world is about 7 billion. And if people want to screw your website up and they have 3 devices and they're trying to talk to your device, let's just multiply that by 3. Right? The finite number is there, right? I mean, if you think about it, 1 billion hits a day is not a very safe number. I was at a client last year at Thanksgiving, and we had 1 billion hits a day. So it's not a very safe number. 10 years ago, that would have been a very safe number. But maybe 10 billion hits a day is a safe number. So again, scalability is not infinite. Most of the times we think of scalability as infinite. The requirements are not infinite. If you know how to take care of 1 billion hits a day, you are already in a good spot. And if you can multiply that by 2 or 3, you know how to scale your website. So let's talk about the concepts a little bit. Scalability. What's scalability? All in all, it means how many requests I can actually handle. When is it that my system is going to break? Performance. How do I handle every single thing I do using the most optimal resources that I have? Responsiveness. What was the time taken per operation? Availability. Now, if you get availability right, you actually scaled. Anytime someone makes a request, did you get back to him with a failure or a success in a desired amount of time? You can always get back to him in 10 minutes, but that's not exactly desired, right? And then what's the downtime impact? If you're down for 1 hour, what does that mean for your business? I've had clients, if they're down for an hour, then they'll lose millions and millions of dollars, especially when it's Thanksgiving, Christmas, or any such day. So the first section of the talk is going to focus on CAP theorem, or consistency, availability, and partition tolerance. What's CAP theorem? How many of you are consultants? How many of you are dev managers? How many of you are developers? How many of all the above? All right, great. I'm sure you've used this a lot of times at work. Cost, quality, and time. You can only get 2. So when your manager pushes you, you tell him, look, you can only get 2 of the 3 because it's a triangle. In the same way, CAP theorem is also a triangle. Consistency, availability, and partition tolerance, you can only get 2 of the 3. So what's consistency? Whenever you made a call or wrote something, let's say, to a database, it was consistent in the sense that if you had replicas of the database, it was atomic. The change was atomic, at the same time was consistent in the sense it means the change got registered at all the databases. That's consistency. Availability, if you made a request, you were able to get something back either as a success or a failure. And partition tolerance, if you have a big system, parts of the systems can die, but still you have your system up and running. What that really means is, if you look at Gilbert and Lynch white paper, it's a very good white paper if you want to read about it in detail. It says no set of failures less than the total network failure is allowed to cause the system to respond incorrectly. So again, if you have redundancy built in, you could actually achieve that. Fallacies of distributed computing. If you ever get a chance, read this article. It's a great article that talks about how we think that these things are actually true, but they're not. We somehow think the network's reliable. It's never reliable. latency is 0. That's not the case. When we run it on our local machines, we're like, wow, this is amazing. We're doing great. But the moment we get onto a network, especially if it's a mobile network, we see the delay. Bandwidth definitely is not infinite. Network is secure. A lot of times we think the network's secure. Well, even till 2014, we get a lot of network attacks, and that's millions of network attacks a year. Topology doesn't change. It changes all the time. You might have the best system in the world. You will have nodes die. You will get into situations where you had a master and you had a slave, and all of a sudden a master died. You elected your slave to a master, and something else happened. We always think there's one administrator, and that's usually the person who's actually creating the policies. But most of the times when things go wrong, he is the only one who's not available. So we have to think about it in a different way. Transport cost is 0. That's not true. And network is homogeneous. And that's, again, not true. You will be surprised. One of the top 10 attacks happens because of security misconfiguration. And that happens because a lot of times people who are putting the servers up forget to use the same best practices they've used already on the previous servers to the new server. And you'll be surprised. It happens. And security misconfiguration is the top 9 attack on OWASP 2014. Section 2, failed architecture. So let's just go and create an architecture and try to fail it. The best thing about a developer or an architect is failing fast. You want to fail fast. This is how we start. There's an app server and there's a database server. What we're going to try to do is fail this thing in theory. You know why theory is important? You know what's an academic? So here's a cool definition I heard about an academic. An academician is a guy who does not believe about something that's running really well in practice until he sees it in theory. And what's a theorist? Another good definition about theorist. A theorist is a guy who is willing to assume anything but responsibility. Right? So whereas we can joke about academics and theorists, the point is, if I have an architecture on paper, I might fail in practice. But if I can fail an architecture on paper, it's bound to fail in practice. So one of the ways I do consulting is I make sure that I actually qualify first on paper. So let's start with an architecture that we're very familiar with. Most of the time, this is how startup companies run. Oh, we got one server. We're good to go. We're going to create the next big Facebook. And we have this amazing server, right? What we're going to do is we're going to put IIS on it, and we're going to put SQL Server on it. We're good to go. What's the downside? The downside is we all know that a database server, what does a database server need? More RAM or more CPU? RAM, very good. It's good to have both, but obviously, you need more RAM as a database. What does an app server need? More RAM or more CPU? But if you were to tune an app server, you'd tune it towards CPU, right? Now, obviously, it's good to have both, but they get tuned differently. So in order to tune an app server, the best practices are different than tuning a database server. But now when you have everything on the same box, you're kind of limited. If you have an app server, you want to optimize the TCP/IP connections, right? Because you're going to get a lot of those. You're going to try to do non-blocking I/O. You're going to try to do a lot of other things, which may not be needed in case of a database server. So we know that this has a limitation, because after some time, what's going to happen? We'll have to go and throw more RAM and CPU and try to make it bigger. This is the way we get around the problem. So if you go back, I had this app server, I had a database server, both of them were part of the same server, and when I had requests that I couldn't handle, what did I do? I threw more RAM and threw more CPU. Another way to fix the same problem is to do vertical partitioning. What did I do now? I created 2 different servers. So the app server resides in one server, and the DB server resides in another server. What's the downside? Very good. So the downside is that I did not actually increase the overall availability of my app anyways. Because it's still, let's say the app server is down, the app is still down. Let's say the database is down, the app is still down, right? So I did help myself a little bit, but I didn't help myself a lot. So it's bound to fail when we get to a point that, okay, one of them fails. That's fine. That's availability. But what about scaling? I'm still limited to the same boxes. What am I going to do? Throw more RAM, throw more CPU? Until I get to a point that either my database server is my bottleneck or my app server is my bottleneck, right? So what do I do next? Load balancers. We have a solution. Good to go, right? That's what we do. Either a software load balancer or a hardware load balancer. Now, you can pick whichever you like. Again, it doesn't matter because what it's doing is scaling this layer, which is, and this is IIS, by the way, Icon. You could put any other server you like. So right here, we can scale this. And this is horizontal scaling, or more like scaling out. Vertical scaling means scaling up, which is what we were trying to do earlier. The same box, throw more RAM, throw more CPU, make it bigger. What we're doing now is scaling it horizontally. Well, so this scales horizontally, but what's the problem? Do you see any single points of failures? Very good. Which are those? Exactly. So it's the database server, and it's also the load balancer, right? So we got two single points of failure. So here's the easy part. Most of the times, computer science doesn't even need to do in real life. You could just do it on PowerPoint. And as long as you can fail it on a PowerPoint, you're good to go. So we know that we have two single points of failure. One is the load balancer, and the other one is the database server, because no matter what happens, we can increase these to hundreds or even thousands of servers. We don't know, right? Depends on how much we need. But the bottleneck still is the database server. So what do we do next? We go back to IT, and we tell them, hey, look, I need more services. And that's how I'm going to fix the problem. And what's the problem with that? So this is what happened when WCF came out. Everyone was like, hey, we're going to fix all our problems. Now we're going to create a lot of these services, right? And they're going to help us. So what does a service help us with? One of the interesting things is that services do not actually increase your overall availability. They do in a way if you actually create them redundant and all that stuff, but if database is still your bottleneck, you're not really helping yourself a lot. What's the downside of a service? I was at a client where we had 9 different departments. And product department, and I'm just making these names, I'm changing the names out of confidentiality. There's a product department, there's a customer department, there's an order department. And they really can't talk to each other because they're controlled by smart managers who don't like each other, right? Typical industry. So now what happens is you say, okay, product team is going to create their own services. That's the set of services. So let's say the service 1 is product service. Then second service is order service, and then the third one is customer service, right? And what we're going to do is we're going to manage this in our own way. Downside now is anytime you were actually supposed to go to the database and do a join, now you're doing the join in memory because you're getting the data out from the services. Somewhere here, you're going to do a join in memory. Do you see a downside? Do you see a downside to that? Exactly. So we have a performance issue right now. The same exact thing which would have easily been solved by going here to the database and doing one join. Now I have to do a cross-service join, maybe 3 or 4 of those, somewhere here in memory. So I'm not really solving a problem, I'm creating another problem. Do I have a benefit? Yeah, I do have a benefit, that I can create services that are independent of each other, and no one has to worry about that, and I can create dedicated teams that can go and work on the services. But I do have some downsides, especially if my business requires me to actually work this way. So let's go and try a less scalable solution. So what's a sticky sessions? Everyone knows about sticky sessions? User 1 makes a request to the load balancer. The request goes to the first server. And next time, I want to know what is the session, because he's in a shopping cart. I don't want him to give me the same information over and over again. So what I tell him is, OK, whenever the next request comes, my load balancer should take me back to the same server. So anytime the same user logins, he keeps coming back to the server 1, and that's called a sticky session. What's the problem with that? Well, the problem is, how do you scale? Because you're forcing the load balancers to go back to the same server over and over again. What is the solution to this problem? Well, what you could do is you could create a central session store. And the central session store is going to have the session data right here. So it doesn't matter where the next call comes to. So maybe you started with server 1. The next call went to server 3. But server 3 can make another call and get the data out of the session store. Now, this session store could be anything. It could be your database. It could be your Redis cache, Memcache. I don't know. It totally depends on how you want to do it and your business. So this is another way of solving the same problem. What's the downside? Well, you still have one session store, and then they're going to have to make another call to, and it's still an internal call, but it's still another call to get data from the session store. There's another way out of it, which is called cluster session management. What do you do here? Well, the same session store is replicated. So the same session is replicated between each other. It can solve certain things for you, but creates another problem that, A, you are replicating the same session data amongst the 3 servers. So you're not really getting the benefit of trying to scale out. But if you have few requests, this is not a bad solution, even though I'll highly recommend this solution over anything else, unless you have very few requests and you can deal with something like this. So now, our single point of failure was load balancer. How are we going to fix that? In order to fix that, what we do is we create another rectangle right here, go back to our PowerPoint and say, OK, we're going to have another load balancer right here. And anytime there's a request, I am going to let this guy handle it. But if this guy is down, the request should go here, right? And that's more like active-passive. Or you could have active-active, which is something like this. It doesn't matter where the request goes. It could go to any of these load balancer, and they can technically take care of it. That's active-active. But now we don't have a single point of failure. We can do this any amount of times, and the load balancers could be increased more than one, and we've gotten around that problem. So vertical partitioning. Now, still, we had a problem with the database server. How do we fix that? Well, we've got something called storage area network. So instead of a database server, now we have a storage area network that's actually going to have our files. The actual files are going to stay over there. They're going to reside over there. So anytime I need to scale up, I could scale up. So anytime you see the word vertical, it's scaling up. Anytime you see the word horizontal, it's scaling out. So in this case, I need more space, I need a bigger storage area network, and I can scale up. Good enough, but there's probably a better solution. Well, maybe what we could do is we could do horizontal scaling of the database. So if I were to go back, still see the bottleneck being the database server, can I actually create few database servers? Maybe I can. So something like that is possible. Now, when I talk about database, I'm actually talking about one specific type of database. It's relational database. So it could be SQL Server, Oracle, or any of the other ones. Now, these are DB replicas, by the way. Do you see a problem with this? Or everyone likes DB replicas? We have any DBAs here? Oh, you're still alive. OK, good. So DBAs still have jobs. Well, good to know. I'm kidding. So that's awesome. DBAs love replicas. Do you love replicas? OK, you don't. Very good. I love you. That's awesome. So there are problems with replicas, right? What are the problems with replicas? You go and make a write to the master, And then the replicas are going to have the same data. So what you have to do is wait till this data gets written to the replicas. Or you don't wait. So if you wait, then you're slowing down on performance a little bit. And if you don't wait, you're not consistent. You're eventually consistent. Does that make sense? Now, you are eventually consistent. What that means is after some time, all your database replicas are going to have the same data. So if you make a call, you can read from any of the slaves, and it's going to give you the data. Question for you. Well, if you're going to go this route, why would you not just explore a NoSQL route? Why would you not explore polyglot programming? How many of you use NoSQL? How many of you use Azure? Have you used table storage, Azure Table Storage? OK, good. So if you have used Azure Table Storage, you've actually used NoSQL without probably realizing that. So now, we're going towards a very scalable architecture. We have the load balancer right here. We have another load balancer right here. And we can add any amount of these. We can take the servers, IaaS servers. We can scale them also. We're good to go right here. At the DB server level, we have a solution. It might not be the most optimized performance solution, but we still have a solution that we can actually expand it, right? And we can scale this thing. And then we have the storage area network. Now, has anyone done database partitioning? Great. Has anyone taken a SQL server or any RDBMS from one server and taken it to another server and had to deal with problems? OK, so everyone's nodding the head. Means you understand the problems. The problem is when you scale up, means keep scaling up in RDBMS, it's not a problem. But when you scale out an RDBMS, you lose the benefits of an RDBMS. Does that make sense? Do you remember you had ints and all of a sudden you could not use ints in the ID? You probably had to use grids or something like that because ints had a limit and you had to partition out. Do you remember that you had problems with the SQL schema just because you're partitioning out? So partitioning out becomes a huge problem when it comes to partitioning out an RDBMS. And what are the advantages of an RDBMS? The biggest advantage of an RDBMS is ACID transactions. Atomicity, consistency, integrity, what is the last one? D, durability, right? So ACID transactions, you lose the advantage the moment you scale out. So when you're scaling out, you're losing that advantage that you already had in the first place. So what do? You come up with a solution which is polyglot programming, polyglot persistence, which we're going to talk about in just a little bit, and I'll show you some demos. But over here, let's stick with RDBMS replicas, and we're good to go. Now, this thing is a DB cluster. Can someone think of how many of these we can have? How many of these DB servers we can have? Realistic number. Do you think I can take this thing and make it 100? Maximum 16. Very good. It's a finite number. Why? Because after some time, you're going to lose the benefit. So let's say you have one master and you have 4 slaves, right? For every one master, you're going to actually have to do 4 more calls to the slaves. So you have a finite number. You can't have one master and 100 slaves. It just doesn't work that well, right? And you're going to wait for it to be consistent. It's going to be slow like anything. So it's a finite number. 16 is a good number. I think 8 is pretty good. Beyond 8, you start losing the advantage. But good to go. At least to start with, it's not a bad idea to scale your app like this. Here's another way we could do something, become a little bit smart about it, and say, OK, well, I have some social data, which is a lot. That's like Twitter data, Facebook table, and all that stuff. But then I have important stuff, which is this: DB cluster 2, users table, products table, and everything that I care about. So keep in mind, I'm a big fan of SQL Server. You want to use SQL Server for important data. Your e-commerce data needs to go right here. Your, anything to do with security needs to go right there. But I don't really care about Twitter, Facebook, or any of that data. Because no one's going to go back and say, hey, what was the post I wrote 10 months ago. No one really cares about that data as much. And even if I lose the post that I put on Facebook 10 months ago, do I really care about it? But what I do care about is, well, how many products did you buy from me? And even that means 10 years ago. If you bought a product from me, I really want to keep that data. Well, in this case, we still have RDBMS. And we're still using a different cluster for social data and a different cluster for my business data, right? We're good to go. But why am I throwing the pointer out? Because in future, what I'm going to do is I'm going to make this the RDBMS, and I'm going to take this and make it a NoSQL or something else, right? And that's where we're heading to. So this is a good approach because I know that these guys are not interacting much with each other. So I can create a different cluster here, another different cluster here, and if needed, I can create more clusters. Simple, good to go. We can scale, very good. Well, maybe there's a different way we can scale. How about going to my app cluster and saying, whenever I have the first million users or the first 10 million users, whatever that is, always send these guys over here. Now, keep in mind, the data is same, except what I'm doing is partitioning according to the users. I'm sure you've done something like this. A lot of companies do this. For very big clients, let me create a totally dedicated system for them. And that could be a DB cluster, right, for this particular client. And then another DB cluster for another client, and then another DB cluster for maybe 5 different clients, because we know that they're never going to go beyond that space, right? So once you are here, you're doing a different thing, but assume you have 1 billion users coming to your website. What you could do is 10 million users on this one, the next 10 million users on the next one, and continue like that. Does it scale? Yes, it scales. I'm sure you all know how Facebook scaled initially. They started, I think, from Harvard, and then they went to Stanford, and what they had was dedicated servers for every single university. Until I think they started later interacting between each other, and they go, OK, well, now we have something else. And then they use their NoSQL solution. Is everyone clear with where we're going? Everyone with me on this solution? All right, so I'm collecting $5 each for the solution I'm giving here. I'm kidding. So this is next, pretty simple, right? Very simple diagram. What we're getting to now is we have a load balancer, and assume there's another one here. And we have this system that is the app layer. We have these DB clusters right here. And this layer can make a call to whichever DB cluster it has to based on some kind of hash map, which is right here. Again, why do we need a hash map? We want to know where do I want to make the next call. And in order to make the next call, I need to know which is the fastest way of me getting data out of somewhere. Let's take an example. Let's say I have electronics data. And all my electronic data goes in this set of servers. And then I have, let's say, my social data, which goes in this set of servers. What I need to know is which particular server has the data that I want. And that's exactly I want the hash map, because it's going to take me there in one call. Does that make sense? I could navigate my way to there, but I want to get there in one HTTP call if possible. Now, if I could do that, then that's great. And that's why I have a hash map. And this is, again, the storage area network. So if you take the DB cluster, the actual files are here. And then the DB cluster 2, the files are right here. But again, you could still have the same storage area network. So what's next? We're coming with something which is actually even more scalable, which is something like this. And this is where it gets a little bit complicated. And again, a lot of what I'm talking about is something out there. People talk about it most of the times. And it's nothing new. This is computer science. This is how people evolved into creating solutions for their enterprise when they had to scale apps. Now, there's one constraint, though, that it's all dependent on an RDBMS scaling. And we will look into a different way of doing the same thing later. Right here is a global redirector. And these guys, if you look at these big rectangles, that are serving set of 1 to 10 million users and 11 to 20 million users, they're 2 different sets. What we could do is we could separate these sets, and then we could scale these sets. We can have any amount of these sets. Right here, we have the same solution. We got the load balancer, we got the IIS, we got hash map, which is actually telling us where to go, how quickly to go to get the data we want to get. Then you have the DB clusters right here, and then you've got the storage area networks right there, where now we have a way that we can scale this set over and over again. Is everyone with me here? Good to go? Looks like we have a solution. And then there's a global lookup hash map. Well, who is actually telling me to go to which set? And that's part of the global lookup hash map. That tells me where to go. And then there's a lot of other things you could do. You could add caching. How many of you use caching? Everyone. Very good. How many of you use object cache? Session cache? API cache? Page cache? What level of caching? Do you do L1, L2, L3? All of them? Okay, good. So here's one thing I've noticed in my consulting experience. A lot of people know what to cache, but they don't have a policy about what not to cache. And it's very important to make sure that you have a policy regarding what not to cache. I don't know if you remember, a few years ago, about 4 or 5 years ago, everyone who was doing a jQuery presentation would do a $.post to get a get. For a get resource, they were putting a lot of $.post. What that really meant was you are making sure that this resource cannot be cached because post can't cache, right? So small things like that are important. Time to live, expires headers, and a lot of that stuff on your web app is very important because you want to make sure that you're caching, but you're only caching up to an extent that you want. There's a study that says 40 to 60% of the users, every time they come to a new website, they come up with an empty cache. So basically, they really don't have anything when they're coming to your website. So what do? You make sure that the home page that you have gets populated fast. I'm going to give you an example. It's revolutionary. It works. I go to your website. You have a product that I'm interested to buy, and you're selling me a monitor, 24-inch monitor. You have this home page that loads a lot of things, but I'm only interested in the 24-inch monitor. What I would like to do is just go right there to your website, sit on your search box, type 24-inch monitor, and I really don't care about what's loading in the rest of your page. I want to go to the search box, type 24-inch monitor, and get my results out. What does it tell you as a developer? As a developer, it tells me one thing, that my search box should be good to go before I even do document.ready. Before I even load my page, my search box should be good to go. What is the second thing it tells you? It doesn't matter what you're populating. All that matters is what the user wants, right? Now imagine you have a same website, but your competitor has a different website, very similar, but it loads very fast, and it tells me, okay, well, these are the 10 24-inch monitors we have for you, and they got loaded in 200 milliseconds. Whereas you have some awesome images on your homepage, and it takes about a second to get there. We've already talked about 200 milliseconds is a good enough time for a person to start feeling that he's not liking the website. So what's going to happen is, anytime this happens for 2 or 3 times, there is a chance he's going to leave your website. So let me give you a solution. Why don't we do something like this search service actually talks to a search database, gets the data back, renders all the 10 24-inch monitors, right? And the data is not coming from an RDBMS. It's just coming from a search service. It could be an Elasticsearch, Solr, Fast, Lucene, whatever you want, right? When I see these 10 monitors, I look at the price that I like the most, and I want to look at the details. So I click on the details. When I click on the details, it takes me to a different page. On this page is where I'm actually loading the real pictures. Remember, the first page, I was only loading thumbnails. I wasn't loading the complete description. On the second page is where I'm loading the images, and I'm loading the description. Where is that data coming from? The second page could be coming from a NoSQL database. And it's a pretty extreme example, but there is a reason behind why I'm giving this example. Now when I look at the second page, I go, yes, exactly, this is the monitor I want. What do I do next? I'm going to go buy it. The moment I hit Add to Cart, the third page is coming from a SQL Server. Do you see the method behind the madness? And it's pretty revolutionary, but it works. I can guarantee you one thing. If your first few pages are slow, you have a chance of losing the customer right there. There is a reason why Amazon makes a lot more sales than a lot of other competitors out there, because the user experience is amazing. On the same exact thing or the same exact price that the other person might have to offer. Is everyone with me on this? I do not care about my data on the first page or the second page as long as it gives me enough data that it's searchable, which is the first page, right? And why did I say search database? Why did I not say NoSQL database? And I'll give you an example later. I'll show you in code why it matters. There's a reason. Because if I'm populating my first page from the search page, I can do certain things like more like this or recommendations. Have you ever seen a recommendations page? Recommendation page comes up because of an algorithm that works behind the scenes. And that algorithm is easy to implement in Lucene or some of the search databases compared to any RDBMS. What if I want to boost something? For example, your company could have a sale going on a 27-inch monitor. And when I looked for the 24-inch monitor, you wanted to boost the 27-inch monitor sale right up. It's one setting in a search database, and it's a whole lot of programming in an RDBMS. So now you showed me 10 results, out of which one was a 27-inch monitor, which is on sale. Now the customer, who's me, is looking at it. I'm paying the same amount for 24-inch and 27-inch. Why should I not just go buy the 27-inch monitor? Right? So the first page comes from a search, and so for search database, the second page comes from a NoSQL. Why is that? It's a lot of text. And NoSQLs are good at what? Reads. They're eventually consistent, but they're good at reads. How many of you will actually keep changing your inventory every second? You're not going to do that. The specs of the monitor don't change overnight. If LG doesn't change the specs of a monitor in a year, the same monitor, you are not going to change it in your database, right? So you don't have the worry about losing it. Why is the third page a SQL Server? Exactly because now you've locked the customer down. He's not going to leave you anyways. Now you could worry about security. You could worry about acidity. You could worry about your data. And that's exactly when you use a SQL Server. Again, the biggest benefit of this is that on the first page, you're taking about 30% of the traffic, moving it towards a search database. And then you're taking another 20% of the traffic and moving it towards your NoSQL database. And then you're left with just 50% of the traffic that actually goes to SQL Server. So you're actually scaling your app without realizing what you're doing. So there's a big advantage. It's not just performance, it's also scale. And all of you know that it's easy to scale out a search database or a NoSQL database over an RDBMS. But keep in mind, I am not saying you can do away with your RDBMS. It's still important. It's very important. It's a need of the hour. You have to keep it for the important stuff. Now, caching could be used on that same page too. If you already have a lot of that stuff that's going to be pulled in again and again, why not cache it? And you could cache it using Redis, Memcached, or any other thing that you like. HTTP accelerators, this is also a very good idea. Now, if you are going to use an HTTP accelerator, you get a lot of benefits. You could take your static content and you could redirect that to a lighter server, right? You could cache your content based on different kinds of rules your company specified. You can also use non-blocking I/O and do a lot of other things, and it's a good idea. Now, keep in mind, there are other recommendations that we talked about in the beginning from the blog post where they'll talk about CDNs, a lot of that stuff, which you can anyways use too. So CDN came up anyways, IP anycasting. Do you know what that means? So basically, you have a prefix, IP prefix. So everywhere, you can have multiple servers around the world, but you have the same IP prefix. What's the advantage? Well, let's say you have a server in Spain, and it's getting hammered a lot. you could technically create another server, and all you do is route the traffic to that server just because it's in proximity to this new server, and that's IP anycasting. It's a good technique a lot of people use, very, very successful and helpful. We all know what async non-blocking I/O is. I don't know if you've done .NET 4.5. You see some of that come in as part of .NET now. So you could technically do something like that. We already talked about L1, L2, L3 cache, and then grid computing. Let's see some demos. So I'm sure we'll have some time for questions. So here's an example. What I'm doing is, it's a very simple example of the same database, about 20,000 records, and I'm going to make a query. And what I'm trying to do is to use two different technologies. One is a NoSQL database, and the other one is a search database. And both of them are running on Azure. Now, you could run it anywhere, but again, I just wanted to pick one NoSQL database and one search database. So what I'm going to do is show you the data set, which is this. I've got address, and then the partition key. In this case, I just called it address because it's just 20,000 records. And the row key is the address ID. And the address has city and just address line 1. That's it. So what I'm going to do is search using city, right? I typed in Paris. I submit. It takes about 842 milliseconds, by the way. So the count is 50. I'm locking it down to 50. I'm not getting any more than 50 records. And the time taken is 842 milliseconds, right? This is using Azure Table Storage, which is a NoSQL database. Well, we're going to go back, and we're going to do the same search using Azure Search. So you see the difference. The same exact records come back. It's 338 milliseconds. And I'm typing in the same exact data. There's a lot of difference. You're saving about 500 milliseconds right there. Now, we're going to go back and do something different. I'm going to type Paris. I don't get anything back. The count is 0. All I did was make P lowercase. Is everyone with me? What I'm going to do is I'm going to do the same thing right here. Paris, lowercase, submit it. I still get the same data. I'm trying to make a point across here. Most of the times when we choose a technology, we get logged into that technology. And what we try to do is we try to use the NoSQL as a search database because somehow we think there is SQL and then there is NoSQL. We don't realize inside NoSQL you have different kind of databases. There are databases which are good at caching, which is Memcache, Redis, Oracle Coherence, a lot of those. And then there are databases that are good for searching, which is Solr, Elasticsearch, fast. And then there are NoSQL databases that are good for document databases, which could be Raven, MongoDB, Riak, Cassandra, and they're all different too. And then there are different NoSQL databases that are graph-oriented, for example, like Neo4j. So there are a lot of different NoSQL databases out there. And now there's another movement which is called NeoSQL. So it's not like NoSQL, but it's kind of SQL, but like new kind of SQL. So there's a lot of those out there, right? And it gets confusing after a time. Well, I want to go back and show you something else. Now, what if I wanted to search for address? Line 1. You see, the previous search is actually only searching the city, right? And I want to be able to search Paris regardless of Paris being part of my address line 1 or Paris being part of my city. Because I could actually have a Paris street. And I really don't know what I'm searching for because I'm on your website. I'm a user, and I'm pretty dumb. I'm not calling users dumb, but I'm calling myself dumb. What I'm trying to say is you may know your business really well. I may not. So if I'm on your website, I might be searching some things which I have some clue about, even though you know your domain really well, right? If I am searching auto parts and I'm not the most qualified person to know about auto parts, I am going to search not the exact auto part, but I will have a clue to get to that auto part, right? So what I want to do is search for something that might lead me somewhere else. So if I come in here and say search any field using Azure Search, and I say Paris, do you notice that this is even less time than what it took when I was only searching the city table? That's exactly the point I want to make. Is everyone with me on this one? It only took me 282 milliseconds in this case. And I'm doubling my search. Right now I'm searching address line 1 and city. Previously I was only searching city. Does that make, am I clear? I'm doubling my work and my time to do the same thing has decreased. Why? Because the search service is specialized at that part. And I want to show you the code that it takes to get that going too. So let's see the data that comes back. I've got Paris Lane over here, and then I've got Paris City over here. Anytime you see Paris, it's searching it, regardless of it being in a different field. It's searching it right. So let me take you to the code. No way. Somehow got disconnected. Okay, no worries. So in this case, if I were to show you the code, and again, don't take me on it, it's the easiest way to make a query, and I didn't write some awesome code, so this is some dirty code right here. What I'm doing right here in case of table storage is giving it the partition key, which is address, a lot of hard code. You know, these are my credentials, and all I'm saying is look for the city and give me the exact match. The next thing is this guy. This is where I'm actually making a REST call to my search service. And all it does is says, look, I'm trying to search the field specifically city. In this case, I was only searching city. And the search term is whatever I pass in. That's it right here. And then the third one is where I actually remove this line. All I did is removed the search fields right here. And I just search for the city, and it searches every single field which is marked searchable. And in order to do this, all I had to do was when I created my index, I had to say searchable equals to true. That's it. But if you had to do the same thing in Azure Table Storage, which is right here, you would have to create something called has prefix term, which would have meant you had to write your own expression here. And what does that really mean? What that really means is that if you had to write an expression like this, you are going to compare the prefix with every single row key, and your performance is going to go lower than what it was. In the first case, it was 832 because it was doing an exact match. Now, if I'm not doing an exact match, you're talking more than a second right there to make a call. And that's a lot of time, right? Just to grab 50 records, that's a lot of time. Now we are developers. We like to solve problems. And we go, no, I can make a NoSQL a NoSQL document database like a search database. And that's actually a hack, but I can make it work, right? We say this. Good. So for that particular reason, I want to show you something else. Well, what if we have different requirements coming, where someone really wants me to go and build something cooler, which is a little bit different. So here's an example. Now, I was supposed to not put pictures from outside, so I had to bring my own website here. So what I did is, if I go to something like this, I am a user on this website, and I go, OK, well, I want to look into mudras. I click on it. Oh, I could not find what I wanted to. This is not good experience. So if I go, OK, let me look at the asanas. Oh, I could not find what I actually wanted to. So what do? Well, we want to give him a search box. But what we don't want to give him is multiple search boxes for multiple categories. So my boss comes and tells me, I want you to give me one search box that searches everything. OK, great. So let's do it. So the moment I type A, you see I've got asanas, I've got mudra, I got pranayam, and I got my blogs. So it's searching all the different categories for me. Now, can you do this in a NoSQL database, a document database? Yes, you can. But is it worth your time? Probably not. Because in a search database, it actually supports it out of the box. And all I have to do is a little bit minimal coding, get all the data and condense it together and show it to someone like this. And then if I go click on one of these, I could technically get to that particular data. And if you look at the speed is amazing. Have you seen autocompletes where you actually are waiting and you don't even know it's an autocomplete until after you've already found what you wanted, right? And that happens too. Imagine, what if you have millions of hits going on the website? What happens to the same autocomplete now? It's actually very, very, very slow, right? Now, if you look at this guy, all I'm doing now is typing in something that is actually not even there. If you look at the first record that pulls up, it's a Sanskrit name, so it's a little hard to pronounce, but it's Ardh Chandrasan. What am I doing here? I've ended up collapsing the first word and the second word, but it's still showing me the record. If I was in a document database, it would not have been that easy. I would have had to write code to make it full text searchable or something like that. And there would have been a cost associated with it. So use the tool that is the right tool for the right thing, because there is no one size fits all. This is 2014. We have billions of devices going around us, and it's not easy to continue using the same practices that were best practices 10 years ago. So if I were to show you the code for this, it's very simple. It's MVC. I have 4 different repositories. Again, they're actually talking to the search database. I use dependency injection right here, so I get references to all of these objects. I come in here, and I say, here's my search request. You can start searching from 0, in the sense my autocomplete can start the moment he types in A. It's OK. A lot of people do it at the 3rd letter, but again, we wanted to make it simple. And then all I'm doing is 4 kinds of different searches. Then I use async await, wait for that right here, and whatever results I get, I send it back to the autocomplete. And when I'm in the autocomplete, I make sure that I show it per the category. That's it. Now, every category is just showing 3 records. And that's just by choice, because if I want to pull it up on a phone, that's going to be a lot of records. And if I were to optimize it for my phone, I could do something different too. So that's it. All that takes is this. And if you are wanting to look at the code inside here, technically all you have is results right here, which has the same search results. And I could add whatever I want to put in here. Simple. So there's nothing big I'm doing. Now I'm running Elasticsearch right here, right, which is something that I'm using behind the scenes to get this thing done. But that's it. We will take up questions pretty quickly, but I have a few more slides to cover. So finalizing, polyglot persistence is the future. And the best thing I liked about Azure was that I had not used Azure Search or even Azure Table Storage until this week. And when I wanted to create something real quick, I pulled up Azure. It took about $3, and the demo was ready. That's it. So it was good. Here's a good way to look at NoSQL databases. This is the depth of functionality, and this is scalability and performance. So scalability and performance are high right here, and depth of functionality is high right here. So relational databases are here. The depth of functionality is amazing. But when you try to scale them, they're right here, because they can scale up, but they can't scale out. And scaling up is more expensive than scaling out. When you scale out, you could scale out with very little money. Technically, you could have commodity level servers, and you could scale out. Well, so the document databases are pretty much right here. They're very good at pretty much everything that relational databases do, except there are chances you might get into trouble with the things database is really good at, like acidity, right? You might have problems with reporting and a lot of that stuff. So It scales really well. It has a lot of functionality. But again, depending on what platform you choose, there have been problems with some document databases. They even lost data. So I would be very careful before you use it. I was burnt myself. But here's where you have the key value pairs and the memcached. So memcached is really very good at performance and scalability, but gives you nothing. I mean, it doesn't give you a lot of depth of functionality, but it does one thing really well, which is take key value pairs, and it's fast as anything. Now, key value pairs are more like Redis, but Redis has a little bit more than key value pairs. It also takes care of your data structures. It also invalidates your cache. Well, it has a mechanism to do that by giving you pub/sub model. So you know, oh, there was a new entry in my cache. So let me send a signal out to all my clients, and they will update my, the data. And so that's Redis. And then there's a lot of these databases that are somewhere here. Those are NoSQL databases. So if I were to pick, search databases are somewhere here. The major difference is that document databases are based on the key, and search databases are based on the value. And that's why they're very good at searching, because they spend more time on the value side of things than the key side of things. So again, you're talking about one search, which is 2, document, which is 3, and then relational, which is 4. But if you have all the 4, you are getting towards a scalable solution. Now, finalizing an architecture that actually works. Right? Whatever we saw previously has problems. But this architecture, I am still to see problems with. I have found this work at least 3 of my clients where we have gone to about 1 billion hits a day during peak hours, peak days. So going back to the same exact thing, we've got active, active, or active, passive. Totally depends on how you want to do it. We have IIS right here, right? We've got the hash map right here. And we have DB clusters and everything. This is where I would put a document NoSQL database. Why? Because if I'm taking data which is not very important to me, which could be data like description and a lot of that stuff about the catalog. It could be data which is social data or anything like that, which I'm not losing any money on. Put it this way, anything with no liability, I'm going to use this kind of stuff, because it's not just one master-slave configuration. It could be any amount of masters, any amount of slaves, right? The data that's more important to me as a business stays over here. This is my relational database, and that stays over here. And then I have a search database, and this is important because, again, if I want to do something really fast, now keep in mind, a lot of these search databases do not even come with any security whatsoever. They do not come with encryption whatsoever. Think of this as something that is like an inverted index, which really comes to the RAM of your server, and it gives you retrieves data fast. And when you have autocompletes and a lot of that stuff, recommendation engines, right, things that need to be there but don't have to be super secure or anything, you could use this. So again, this is scalable. This could be scaled out, so you could use this too. Now, keep in mind, I would never use this as a system of record. And a lot of the companies who build this kind of technologies also will tell you not to use this as a system of record. Why? Because you cannot trust this. The benefit of this, you could have the same data here and run something called a populator or indexer that can recreate these indexes real quick. A lot of times it's a matter of about 10, 15 minutes that you could recreate the whole indexes. That's it. Yeah, you'd be surprised. That's a lot of data that's going to take 10, 15 minutes. If you have very little data that needs to be searched, it might even be like less than a minute. So you can still fall back on this database as the source of record for the search database, but when you're making a call, you're actually making a call here, not here. So this way, you are protecting your SQL Server from being hit more, right? But the writes are still happening here. Now, what about queuing? Queuing mechanisms are very important. A lot of people talk about this in a different way. Asynchronous. What does asynchronous mean? Asynchronous means, well, I got your order, you ordered on our website, you're good to go, and you can leave the web page. Great. Now I'm going to take your order, process it internally, right? Question, when and how do you determine something needs to be asynchronous? Put it a different way. What would you do? How would you make something asynchronous? If you have an option to make something synchronous or asynchronous, which one would you pick first? Synchronous? Why is that? It's simple. Very good. That's a good point. Now, are there people who will pick asynchronous first? Because both answers are right. There's no wrong answers. I personally do it this way. Anything that could be made asynchronous, make it asynchronous, starting from day one. Because one of the biggest mistakes we make is we start with a synchronous system. Everything is synchronous until it stops performing, and we go, let's make this asynchronous. There is a huge benefit of making something asynchronous if it can be made asynchronous. What's the benefit? You have no liability. You're not pissing someone off. If you have something synchronous, someone who's waiting on it is not liking the fact that he has to wait on it. But obviously, now if you're making, you're checking out a cart and all that stuff has to be made synchronous. But if you can make something asynchronous, for example, here's your order, I'm going to process it offline, make it asynchronous. Because asynchronicity has one major advantage, that you don't have to worry about real time getting back to the customer. You can send him an email saying, hey, I can get to you. Here's an email, your order is processed, come back to my website, and now do the synchronous task. So one of the benefits that I saw going towards asynchronous route in the last few years was that I saved a lot of the traffic that was going to go to my actual server in real time, and I could use background processes in different servers to make the same thing happen. And I was not blocking anything. So I think if I were to pick, make your code asynchronous first. This is a search database. Again, you see that we're making calls to all the 3 different ones from here, right? What's the benefit of these 2? Moving to cloud is very easy if you have something like this. So in future, if you want to move to cloud, you're already scaling. All you have to do is now take these VMs and throw them to cloud, and you could scale. This could still stay on-premise. A lot of people will say, move everything to the cloud. Well, if you can, do it. But if your business doesn't allow, maybe you still need to keep this on-premise, and you might have some restrictions. But this solution works. It's futuristic, because you can scale out in the cloud too. So caching is very important. You should never, never, never forget this. This is an integral part of your system, and queuing is very important. So that's offline processing and queuing. This is very, very, very important. And again, what do you use for this is important too. A lot of the open source technologies that are out there don't perform that well. And I can give you examples offline when you're done with this. You've got 6 minutes left, but I can tell you examples where we saw problems like, it was taking 4 minutes to process the requests that were there from last night. And some people thought it's activity, it's real-time activity. And we had to write our own system, which would do the same exact thing in a few seconds. Because sometimes, let's say you're in stock exchange, and for 4 minutes you keep thinking these are new records that are coming in. You will think, oh, the market's hot, but it's not, right? And you're getting a wrong impression of what's not actually happening. And that was happening because probably someone wrote a queuing system which was not performing very well. So again, it's an important question, how important that queuing system is. And if it is, then what are you using for the queuing system? And does it take care of performance? And that's important. Now, queuing systems can scale, but performance is different than scale. They may scale well, but they may not perform really well. And I think in our case, the challenge was performance. So using NoSQL in the right way. A lot of people would go to NoSQL with a SQL back mindset, right? Again, they don't compete. My whole talk is about this, that all of them are complementary to each other. But the problem happens when we take a data from a database, which is a RDBMS, and then we move to a NoSQL with the same mindset. So here's the problem. Something like this, we got account, we got ID, account number, and then we have checking account, we've got savings account, and something like this, right? This is how it needs to translate in the NoSQL world. You see that now I've taken 3 different tables, combined them into one document. Again, I would not call this a table. I will always think of this as a document. Why am I saying that? When you make a call to the SQL server, it's easy to do a join with 3 different tables. Good to go. You're good. But in case of a NoSQL, all you have to do is make one request, get the whole document out, and you're good to go. And since you do not care about the space anymore, which you do care about in case of SQL Server, you do not care about space anymore, so you could actually duplicate the data. Right? I could have the same exact thing with a different key. I don't care, because all I'm going to do is make a call again to only that particular document. So even if I had this document redundant with 3 different keys, anytime someone is making a call using the ID, I'll go here. If he's making a call using type, I'll go to the next one. If he's making a call doing minimum balance, I'll go to the next one. Right? Keep in mind, we can waste space in case of NoSQL. So the good practices in case of SQL do not apply to NoSQL. Same thing, we got account, we got type, settings. Again, it's a flat document. Now, a lot of people go and denormalize SQL Server. If you have the option, why not just go the NoSQL route? Here's another example, indexing a table. I've got employee ID, and you have email, and then you have state, and then you have department. Now, we already talked about this, that we can duplicate our data. So how about creating something like this? We go take the state right here, and based on the state, I take my employee IDs and put it right there. So if someone is searching using a state, he only goes here. Keep in mind, they're not connected. They don't have to be. Right? My hash map is telling me exactly where to go. So he's going to come to this document, get CA, California state, and you're good to go. The next thing you could do from the same table is take your department out and give you all the employee IDs right here. Right? Makes it very simple. Your querying is very fast. What's the benefit of a SQL server? When you are writing to few different tables, it's easier to write because you could do a join and you could write to it, right? In this case, you don't need the join. You are retrieving. NoSQLs are good at retrieval, so when you're creating your data, create in a way that you're good to retrieve. It's fast to retrieve. Here's a good example of what I call not understanding data right. I was part of this company where we had a country, and then we had states inside that country, and this is just fake data, and then we have cities, and inside cities we had properties, and inside properties we had facilities. Right? And someone wanted to see what all do I have. So what does he do? He makes a call to the country level, gets all this data out. There are 2 ways you could do it. One is get all the data out, page it, do something with it, right? That's one way. The second way is you do lazy loading. How many different calls you're going to end up making if you do lazy loading? And guess what? The CEO only wanted to see one property, and that's it. And he was out of it. But your system kept doing a lot of processing. So taking something like that big, condense into one flat document of what you actually need. Maybe all I needed was this, which is facility name, facility ID, and that's it. Maybe that's all I needed. Now, since I can create duplicate data or duplicate documents, it's okay for me to do this because I can scale out with commodity level machines, so I'm not paying a lot of money. Well, let's take another one, which is called composite key. If I wanted to grab some data out, I could use few different things. I could use the department, whatever, it's got software, and then I've got an ID over there, which has data like this. So if you were to focus only on this part, tomorrow my IT department has so much data that it needs to go beyond a server. What we do is we take all this data, put it in a totally different server. And that's where the partition can happen. And I could do the same thing with my sales data, and that's my total data. Very similar, I could co-locate a lot of this data. What if this data was for Europe? And then what if I have some different kind of data for Asia and some different kind of data for America? What I could do is I could co-locate data based on how I had it in my servers. Inverted index. If you look at employee ID, city, department, all that stuff, I could do department IT, and then I could do department sales, and I get all the IDs right here. And then I could get all my cities right here, and then I could take the IDs right here and combine it here. Another way of looking at data, think of these as servers. Every single of these boxes you see are servers. And we're going to take the left-hand side of the servers, this particular area. In order to get to TV, all I have to do is make one call and say entity TV, category electronics. Now you can look at this as a tree, or you can look at it in a different way. In order to get to LCD, I don't have to go to TV. It's a server. In my hash map, all I need to do is specify this, and my hash map is going to make one direct call to that server, which is LCD. I do not have to traverse the tree to get over here. This is just my way of showing you how we can solve this problem. Now, if you can solve a problem on PowerPoint, at the end of the day, it's just an algorithm. Now, if you start using binary search on it, you're going to take a while to get there. But if you understand how to create the hash maps, you're making one request to get to LCD. The same problem solved in a different way. It's just a pictorial representation of the same problem in a different way. Servers 900 to 1,000 will only have cellular data. Servers 8,000 to 13,000, and it could be any number, right? You can have any amount of decimal numbers here. It's not just server 9 and 10. You could have 9.133 or whatever. You can scale this to whatever amount of servers you want to put in. So servers 8 to 13 will only have phone data. You know how to get to the phone data just by looking at it a different way. Now, was it the same description? In this case, it looks like a tree, and actually it wasn't. It was the same exact thing, like what it is here. But just looking at the problem in a different way, we know how to make our retrieval fast. We know how to make one direct call to cell server to get the data we want. Another way of looking at the same exact problem is this. I've got electronics. Electronics spans from 1 to 14 servers, landline from 11 to 12, cellular data from 9 to 10. Again, we can add any amount of data, right? So this is the NoSQL paradigm that we could use and fix the problems that we have when it comes to scalability. Pretty much the last one, flattening the nested sets. A lot of people will take data like this and then come up with stuff like this, where you have skills which Hadoop, Node.js, Spanish, or whatever. I don't have any Spanish skills, by the way. It's just over there. The problem with this is now you will get to skills, and then you will actually have to do some operations on this to get what you actually want. You're going to have to split it, with commas and all that stuff, and get the data. But if you had something like this, all you have is a key value pair. You can get the same data out in one call. And that's what we're trying to do. We're trying to shorten the work we do and make our retrievals fast. The references are right here, and there's a lot more than that. I definitely recommend reading some of this stuff. It's really good. And I think we're out of time, but I'm open for 1 or 2 questions if you want. No questions? That means the talk was amazing. Kidding. Sure. So it totally depends. If you want to migrate from NoSQL to SQL, and if you have a business case to do it, then it's when you know that your SQL server is not getting hit as much. It totally depends on how much traffic your SQL server is getting. I think the question was, when is a good time to migrate from a NoSQL to a SQL solution? If you need joins, if you need security, if you need a lot of those stuff, and you want to move the data over to SQL, that's always an option. We could do that. When is the time to move from SQL to NoSQL? I think the answer is that you have to segregate the data that you think can actually end up in a NoSQL database without spoiling your business. And if you have that, then you have a business case of taking that particular data out. And what you have to do is at the app layer, make sure now the new data is being written to the NoSQL database. That's it. Yeah. Right. Oh, I see what you're saying. So I think in one of that slide, so the question is, one of my slides had, the first 1 million users were part of a NoSQL, and then the next million users part of the SQL server. Actually, it was a different slide. It was actually the one where I had social data as the first slide. So if it's social data, you can go there. But you know that in your app server. In your app server, you know that this data is only social data. So let me send it over towards one side, which is NoSQL. And then let me send the data, which is secure data, towards the SQL side of things. And we can talk about it in more detail. I'm going to be available over here. Thank you so much for being here, by the way.